And similarly, I know here there are like, oh yeah, no, this I cheated. Yeah, there's a summation 2 times summation k is equal to 0 to n minus 2, and 2 times summation k is equal to 0 to n minus 3. But it doesn't matter as n goes to infinity. Yeah. Yeah. Okay, r infinity of k, and again I'm splitting this into like r of minus 1 and plus 1. Yeah, so I call this sigma c square, right? Yeah. So again, like, what's the use of calculating such a quantity? Now, what we wanted, again, I started with saying that your goal is to estimate this pi of c using 1 over n summation k is equal to 0 to n minus 1 c of xk, and the question is how large you want capital N to be. So this gives you an answer for that. So what we have here is limit Zn, right? So I've just substituted, like, there's a square root of n then here, and there's a n over here, and yeah. So this is nothing but just like plugging in that over here, and what we have is, like, as n goes to infinity, that will converge to n power minus half times z infinity, right? And the z infinity is like it's a Gaussian with mean 0 and variance sigma c square, and the sigma c square is given by that over there. Okay, that's it. So times random variable w, where w is c, where w is a it's just white noise. So basically what this is saying is, if this variance sigma c is huge, sigma c square is huge, then n will have to be that, like n will have to be like so you want n power minus half to be like, I don't know, much bigger than sigma c basically, right? Which is like n is much greater than sigma c square. 1 over, there should be a 1 over somewhere.
N power minus half is much lesser than
Yes, and then that, yeah, n should be, no, wait, what is,
you want that quantity to be small.
huh?
You want that quantity to be small.
Yeah,
Yes.
you want this whole thing to be as small as possible. Yeah, so anyway, it's to be less than epsilon. You want sigma c to be like or sigma c to be, huh? Yeah, so n should be greater than like sigma c square by epsilon square if you want an error, this thing to be less than epsilon. Anyway, huh? Yeah, no, this is not the variance. That's what maybe I should have stressed that earlier. This is the asymptotic variance. It's not the same as the variance of xk square in the in the limit. Yeah, it's asymptotic variance. This is what we call the central, or yeah, this is the asymptotic. Yeah, it's funny, like that is given by the CLT. So we write papers using these things, and people don't know what it means. It's like they ask what's the definition of asymptotic variance is, and I don't know how much time I have, but like it has a lot of applications, like minimizing that quantity over there. It's like in so many applications, including MCMC and in reinforcement learning and stochastic approximation. It's pretty big. So I have 5 minutes, so let me take a look at like a very simple example. Again, this was a homework problem, I think. Alpha xk plus wk plus 1. Very simple problem. So wk is, say it has, let's say Gaussian, I don't care. Take expected value of xk, you can show it to be like equal to 0, and then expected value of xk square. I'll call this sigma xk square. This is all from your homework, I think, homework 2. Sigma xk square can be written recursively. I might be making mistakes, but as k goes to infinity, the limiting variance, so x infinity will be distributed according to square divided by 1 minus alpha square. So this is the variance of this limiting random variable, but it's not the asymptotic variance. Now to calculate the asymptotic variance, let's take a look at like what each of these r of k's are. I think you can show that r of k comma k plus 1 is equal to expected value of 1 times xk. So again, in this context, let's c of x is equal to x. Okay, let's say you're trying to estimate the mean of the mean of this function x, and we're interested in calculating asymptotic variance, and it's r of k comma k plus 1 is expected value of x of k plus 1 k, and I think you can show it to be alpha times alpha times sigma infinity square. Okay, because as k goes to infinity, this is the variance, and similarly I think you can show that r of k comma k plus j is given by alpha powered j times sigma infinity square. Okay, now using this and this and this, you get a formula for the central asymptotic variance. Sigma squared, the central limit theorem, is given by summation k is equal to, I should use j because of this j here, plus infinity alpha powered j times sigma infinity square. Okay, that's nothing but 2 times summation 0 to infinity alpha power j sigma infinity square. I've calculated j is equal to 0 twice, so I have to subtract off minus, I think, sigma infinity square, anyway, and that you'll get like 1 by I might be making mistakes, but amount of time by 1 minus alpha times sigma infinity square minus sigma infinity square and substituting this over here. Okay, so this is the asymptotic variance formula. Okay, and this is the variance of this limiting random variable. So, and if you take a look at this thing over here, if alpha is close to 1, maybe I'll write it over here. Okay, if alpha is like super close to 1, you can see this blow up, right? And then if you take a look at this, oh shit, n has to be bigger than sigma w squared divided by 1 minus alpha, the whole square into 1 by epsilon square, right? And you can see that it blows up with alpha. So yeah, basically what this is trying to say is if alpha is super close to 1, then to get a estimate of expected value of x using just these samples which you simulated in your homework, you want n to be like this big. And yeah, if your alpha is like 0.999, then you can imagine n to be like super big. And if you didn't see good results for smaller n, then this is the reason. So anyway, yeah, I'm out of time. Actually, I have any questions?
So the reason we use asymptotic variance is to figure out the bound on n?
Yeah, that's one application. Yeah, it'll tell you like how large n has to be, and more than that, like often you'll get a clue as to how to design this alpha, for example. I mean, in this example you couldn't, but so let's say there are like, say in MCMC, for example, you can generate Markov chains in multiple different ways to get the same stationary distribution, and some way of simulating the Markov chain might have like much lower asymptotic variance than another way of doing it. So and this is like one way to design an algorithm or whatever so that your variance is lower, and or you need lesser number of samples to get convergence. Okay. Thank you. Oh, I have some exams